10 times hotter than the sun. You heard that right. The journey to nuclear fusion for clean energy is nearing its end. The artificial sun achieved a temperature in sharp contrast to the sun with a recent breakthrough. Welcome to Electric Exclusive. We'll be looking at the breakthrough in the artificial sun. China has been at the forefront of achieving clean energy through artificial sun nuclear fusion. The sun in our galaxy produces energy through a nuclear fusion reaction. The hydrogen atoms collide and fuse at extraordinarily high temperatures, roughly 15 million degrees Celsius, inside the sun due to massive gravitational pressure. 600 million tons of hydrogen are fused every second to form helium. During this process, part of the mass of the hydrogen atoms becomes energy. The principal energy sources currently used around the world are coal and natural gas. However, both commodities are in short supply. Nuclear fusion has been touted as the holy grail of clean energy production. However, it remains a long way from being realized outside of a lab. Despite decades of research into the technology, nuclear fusion reactors combine atomic nuclei to generate large amounts of energy that can be converted into energy, simulating the physics of the sun. The process requires no fossil fuels and leaves behind no hazardous waste materials, unlike the nuclear fission process that powers commercial nuclear energy production. Fusion reactors are thought to be safer than nuclear reactors at the moment because, in the event of an accident, they will immediately shut down and stop the thermonuclear process. Why is China building one? Apart from having billions of dollars to spend, China's aim is to harness clean energy. China successfully tested its artificial sun, a nuclear fusion reactor that could generate energy for many years to come if it can be made more sustainable. The HL2M tokamak fusion reactor at the Southwestern Institute of Physics, SWIP, in Chengdu, China, is China's artificial sun. The reactor generates power by compressing hydrogen with powerful magnetic fields until it forms a plasma that may reach temperatures of more than 150 million degrees Celsius, 10 times hotter than the sun's nucleus, and then fusing the atoms together to generate tremendous amounts of energy. Magnets and supercooling technology are used to keep the plasma contained. According to Live Science, ITER includes the world's most powerful magnet, capable of producing a magnetic field 280,000 times stronger than Earth's own field. State media Xinhua reported that the device broke world records after sustaining a nuclear reaction at 70 million degrees Celsius, 158 million degrees Fahrenheit, for more than 17 minutes. The artificial sun is a project dubbed the Experimental Advanced Superconducting Tokamak, or EAST, and is operated at a research facility in China's Hefei City in Anhui Province. A high magnetic field traps heated plasma in a donut-shaped reactor chamber. The purpose of this sun is to provide a vast amount of clean energy that researchers hope to capture to power cities, rather than to provide lighter heat. Because this kind of energy creation, known as nuclear fusion, mimics the physics of the sun, EAST has earned the epithet artificial sun by merging hydrogen atoms to make helium. The process employs atomic nuclei to convert vast amounts of energy into electricity. Since it first became operational in 2006, the EAST has set several records for the duration of confinement of exceedingly hot plasma. Before China's EAST, France's Tour Super Tokamak held the world record for the longest plasma duration time of any tokamak reactor at 6.5 minutes in 2003. South Korea's Korea Superconducting Tokamak Advanced Research, or K-STAR reactor, set a world record in 2016 by maintaining 50 million degrees Celsius, 90 million degrees Fahrenheit, for 70 seconds. According to K-STAR Research Center in 2021, K-STAR set a new record for continuous plasma operation when it maintained a plasma ion temperature of over 100 million degrees Celsius for 30 seconds. However, EAST broke K-STAR's record in 2021, sustaining around 119 million degrees Celsius, or 216 million degrees Fahrenheit, for 102 seconds. Our final target is 300 seconds in 2026, said Yoon Si-woo, Deputy Director General of K-STAR Research Center, adding that the plasma instability is one of the challenges they face. In May 2021, EAST broke a new record by running for 101 seconds at a temperature of 120 million degrees Celsius, which was previously unheard of, 216 million degrees Fahrenheit. The core of the sun, on the other hand, is roughly 15 million degrees Celsius, or 27 million degrees Fahrenheit. The EAST reactor set a new record in June, when it achieved a plasma temperature of 216 million degrees Fahrenheit and also managed to run for 20 seconds at 288 million degrees Fahrenheit. To put this in perspective, the sun's core only reaches about 15 million degrees Celsius, which means the reactor was able to touch temperatures that are 10 times hotter than that. The next goal for the scientists behind the experimental reactor is to maintain the high temperature for a long period of time. This is a step in the right direction as far as China's green development is concerned. Lin Bochuang told the Global Times, "It's more like a future technology that's critical for China's green development push," he said. While this is a huge step forward, Bochuang estimates that China will still be 3 decades away from seeing a fully functional artificial sun. The recent operation lays a solid scientific and experimental foundation towards the running of a fusion reactor, said Gang Zhangzhu, a researcher at the Institute of Plasma Physics of the Chinese Academy of Sciences, who led the latest experiment. The breakthrough is significant progress, and the ultimate goal should be keeping the temperature at a stable level for a long time. Li Miao, the director of the Department of Physics at the Southern University of Science and Technology in Shenzhen, China, told the Global Times. The EAST project, which has already cost China more than £700 billion, will run the experiment until June, and is expected to run into $1 trillion. The International Thermonuclear Experimental Reactor, or ITER, will be the world's largest reactor once completed and becomes operational in 2035, with a peak power output of up to 2 gigawatts. But converting the heat into electricity is difficult because the reactor needs to take a 20-minute break every 2 hours, according to Zheng Kui, chief engineer of thermal systems with the China Energy Engineering Group, Guangdong Electric Power Design Institute of Guangzhou. China plans to start generating commercial fusion power by around 2050, but the fusion power plant will need a unique design with a strong buffering zone to protect existing energy infrastructures from these deadly shocks, according to the researchers. China's fusion reactor will almost certainly not be the world's first, with the ITER in southern France nearing completion and expected to start up by 2025. But after multiple delays since it started in 2007, ITER has become the most expensive international scientific project in history, set to cost the countries involved, including China, between $45 billion and $65 billion. The ITER will be the world's largest nuclear reactor, thanks to a collaboration between 35 countries. According to Live Science, the project involves the United States, the United Kingdom, China, India, and all members of the European Union. The reactor, which is set to start operating in 2025, also boasts the world's most powerful magnetic field, which is 280,000 times stronger than Earth's. The EAST reactor in China is currently being used to test technology for a much larger tokamak reactor being built in France. China's EAST breakthrough is a significant development and the step toward achieving clean energy. According to the researchers, China plans to begin commercial fusion power generation around 2050, which is the deadline for the country to meet its carbon neutrality goal. However, the fusion power plant will require a unique design with a solid buffering zone to protect existing energy infrastructure from these deadly shocks. This brings us to the end of the video. Thanks for watching. Don't forget to like and subscribe. Click on the bell icon for notifications.